start the recording. I'll double click on this. If you double click on the screen, of course. Okay, so linear models, initial value problems. All right, now let me just get my thing here. So in this section, okay, we're going to cover several dynamical systems in which each mathematical model is a second-order differential equation. And this form here, right here, is the form of the differential equation, second-order differential equation, that you're going to see in section 5.1. So you have, that's the general form, okay, with the two initial conditions. And let me just see here. I want to get this off here. Okay, so the function g to the right is called a forcing function or a driving function for the system. Okay, and I mean, let's just go ahead and look at an example here of where that kind of differential equation would be used. How many are aware of Hooke's law? Whoops, hold on, did I? Okay, all right, so very good. Thank you, Matthew. Thank you, Andreas. So Hooke's law says that a spring exerts a restoring force opposite the direction of elongation and proportional to the amount of the elongation. So force, that's right, in physics, Matthew, absolutely. Force equals negative k times s, where s is the amount of elongation. So it makes sense. If you're stretching a spring, okay, the restoring force is going to be going downward. In other words, the force is acting against the spring, right? If you stretch the spring, if you stretch it up, the force is going to act downward. It's to restore the spring to equilibrium. If you well, look, it's easier just to go right to a picture here. Okay, so one moment. Let me get this over here. One moment.
Like in a spring, when you push it down, if you let go, it's going to go back up, and vice versa.
That's correct. That's correct, Matthew. If you push a spring, that's right. And just ignore that noise. Ignore that noise. Okay. Okay. Now hold on here. It's okay. So, all right. So now, force, from Newton's law, force equals mass times acceleration. So what they're doing here, with Newton's second law of motion is, of course, force is mass times acceleration. So m is mass, position is x, so the derivative of x is velocity, and the second derivative of x of position with respect to time is acceleration. So that is being set equal to negative k times x, okay, where x is the displacement of the mass when it's attached to this spring. Okay, so this is a key part of section 5.1. And if we go here to figure 5.1.1, you have a picture of the mass spring system here. Let me move this up a little bit. So the mass attached to a spring. In figure 5.1.1a, the spring is just unstretched. Okay, and that means then that the mass is in equilibrium position. Okay, but if you stretch the spring, okay, the mass then is below equilibrium position, as you see in part C. Now, how do we decide what our axis is going to be? So for a vertical spring, position is going to be a vertical axis, and we're used to thinking of that as a y-axis. But in this class, we'll think of it as an x-axis. So the way this book does this is when the mass is below equilibrium, okay, that the position is positive, x is greater than 0, okay, and when the mass is above equilibrium, okay, when the mass is above equilibrium, you know, that x equals 0 line, then the position of the mass is negative. Okay, so that's our orientation for the mass spring system. How many have seen this maybe in another class, a physics class, or how many have seen this type? Okay, Matthew's familiar with it. And
Are we going to be doing questions where it's going to be vertical? Because then we'd have to take into account gravity, unless they assume that unless we like they specifically say ignore the force of gravity.
Well, we're gonna keep things very simple here. We're gonna be having the
so just keep it horizontal, right?
well, they have it as a vertical
Without
picture,
friction.
but they're not worrying about gravity. Well, I got to be a little bit careful now. Hold on here. Hold on. I want to be a little bit careful about that. Let's get back to that question, okay? Let's get back to that. We'll get back to that. We'll get back to that. So let me see here now. So you can have what's called undamped motion on the mass. So in other words, if the mass is attached to the spring, okay, this is the differential equation for undamped motion. If the mass is attached to the spring and there's no other force acting on the mass, okay, and we assume that we're in a vacuum, and I guess this might sort of reference Matthew's question. So in free undamped motion means the mass will bounce up and down forever. Okay, the mass there's no dampening on the mass to slow it down. So in that case, in the absence, like in a vacuum, the mass just bounces up and down forever. And that's the differential equation, the form of the differential equation here in equation 2 of the, sorry, hold on, where's my thing here? Oh, did I lose the book? Hold on, did I lose it? Hold on, let me get it back. Okay, hang on, let's get it back. Okay, so this is the differential equation for undamped motion. Okay, for undamped motion. But generally, what I like to do, I generally like to, I want to say this the right way. Let me focus on it the way that I want to focus on it here. So this differential equation here, m times d squared x dd squared equals negative kx. Okay, that would model the motion of the mass spring system where there's no external driving force on the mass. Okay, but if you have a driving force, or if you have a force, I want to say this. Well, I want to say it's the right way. This equation 1, again, it models the motion of a mass spring system where there's no external driving force and there's no dampening. There's no dampening. So now, what would the differential equation look like if we had dampening on the mass? What if the mass were, for instance, bouncing up and down in a liquid? Okay, of some viscosity that slows the mass down. How would that affect the differential equation? Well, let me show you. See, I think it's easiest to show the different differential equations. Hold on here. Yeah, this is how the differential equation would be. Now wait, that's not what I want yet. Hold on. Let me go down here a little bit. Free damp motion. Yeah. Okay, so now here, this differential equation here models the motion of the mass when you have damped motion. Okay, when you have damped motion. And you have this extra term, which is negative beta times dx dt. That's added to the differential equation. So the differential equation, hold on here. The differential equation without dampening doesn't have that term, negative beta times dx dt on it. But if you have a dampening factor on the mass, then you add the term. And you notice the term, it's minus beta times dx dt. Dx dt is velocity. Okay, so that means that the greater the velocity, the more the dampening effect will be. Think of it like if you, I don't know if you've ever, like when you were a kid, maybe you're sliding on the floor, and I always think of this because I did this when I was a kid. You know, you're sliding on the floor, and then if you slide on the carpet, what's gonna hurt more? Sliding slowly on the carpet on your legs, or sliding fast on the carpet on your legs? What's going to give you more rug burn? Slow, you know, slow. Okay, Andrea knows what I'm talking about. Going fast on the carpet. Okay, and that's effectively what that dampening turn is. It's proportional to the velocity. Okay, it's proportional to the velocity. So there is then the differential equation where you have the free damped motion. And you can see it's a second order differential equation. And so you can use the technique with constant coefficients, I might add, and right, the velocity is dx dt. And so you can solve this differential equation using the techniques of section 4.4. Okay, the techniques of section 4.4. Okay, now finally, well, are there any questions so far? The signs that you have here, the two negatives on the right side in front of like the kx and the negative beta dx dt, they're there because again, I want to say this the right way. Hold on. I want to say this the right way. One moment. The restoring force acts in the direction opposite of the elongation. Okay, and the dampening will as well. And so if you look at in figure 5.1.1 or figure 5.1.2, the way the mass spring system is, the way the axis is, you need those negative coefficients there. Now, let's go one more here. I want to get to, and I'm not worried about all these cases that they talk about. All we need to do is find the differential equation and solve the differential equation, and we're good to go. Okay, so so I'm looking for the differential equation when we have driven motion. Yeah. So now here's the differential equation. See how it's getting altered? It's getting more complicated as we consider more factors. Here's the differential equation to model the mass spring system when damping is present and you have external driven motion given by a forcing function f of t. Okay, so and again, that's going to be, if you rearrange the terms of that differential equation, that's going to be a non-homogeneous, second order linear non-homogeneous differential equation with f of t on the right side. So and you know, basically this equation here, equation 24, you could just use that equation all the time because it'll sometimes f of t equals 0 if you have no external driving force. Sometimes beta equals 0 if you have no dampening. So it's a very general equation. Okay, and I mean, the book kind of gets a little bit technical with things, but we don't need to get technical. This is the differential equation that we need to deal with. Okay, now something that is also important here, something that's also important is, let me go back here. So I'm just hitting some highlights, and then I want to get to some examples. Let me see here. So for the free undamped motion, okay, the free undamped motion, if for that, if you have a mass that is not there's no dampening present and there's no external force present, then by the differential equation in this section 5.1, the motion, the position of the mass would be x of t equals c1 cosine omega t plus c2 sine omega t. And that makes sense, because if there's nothing to stop the mass, you know, what's going to happen if you have a mass, okay, attached to a spring, and you pull the mass down, and then you release the mass? What's the mass going to do? We'll put it this way: if you stretch the spring, if you stretch it down and release it, the spring is going to then go boing, 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 boing. It's going to bounce up and down. It's going to oscillate. And so thank you, Michael and Matthew. The mass is just going to oscillate back and forth, up and down forever. There's nothing to slow it down. There's no dampening. So when you have the free undamped motion, this is going to be your equation. It's that simple. Okay. I mean, I like to think intuitively here. I like to think intuitively. But here's the thing: this equation, sometimes this equation is not in the good form. I mean, it's fine, but sometimes we want to learn things about the mass. Like, for instance, at what time will the mass pass through equilibrium going downward for the second time? You know, that kind of thing. Well, in that case, we need to rewrite this position x of t with what's called a phase angle. A phase angle. So keep in mind, there's your x of t, and we can rewrite that position function this way. X of t, we can write it as a times the sine of omega t plus phi. So you see, what we've done is we've rewritten the position function. But of course, okay, well, how do we find the amplitude A, and how do we find the phase shift phi? Well, it turns out that if we go down a little bit here, okay, if we look at this figure here, figure 5.1.3, here's the phase shift phi. There's some phase shift. Okay, in other words, I want to say this the right way. When you have a linear combination of a sine and a cosine, okay, you can write that linear combination as a function of just the sine function, but it's a sine function that has to be shifted a little bit. Okay, the shift is that phase angle phi. Now the phase angle phi, okay, is determined by C1 and C2. And what are C1 and C2? Well, C1 and C2 are the coefficients right there for the original equation of motion for this free undamped mass spring system. So it turns out that the amplitude A can be found by just taking the square root of C1 squared plus C2 squared, and the phase shift phi, the phase angle phi, well, the tangent of phi, hold on. Yeah, the tangent of phi is, oh, I see, it's not showing right. Hang on one moment. There we go. So the amplitude is just the square root of C1 squared plus C2 squared. And since the tangent of phi is equal to C1 over C2. And the way they derive this result is they use the addition formula for the sine function. They show it there. It's not hard to see why it's true, but let's just take it on faith for now. Okay, but if you want to look at it, they show in this part the alternative form of x of t. They justify why it's true, and you're going to get an intuitive feel. But keep in mind, if the tangent of phi is c1 over c2, then phi is the arctangent of c1 over c2. But the c1 and c2, you have to respect where the c1 and c2 is located in the xy plane, because you're treating now, based on the picture here, you're treating c1 and c2 like coordinates, okay, in the xy plane. Okay, so I'm really just trying to hit on some highlights here. I want to get to some concrete examples. Michael, I would like you, Michael says, can we write x of t as a times the cosine of? I would like you, Michael, to use, because, you know, WebAssign wants it in terms of the sine. So adapt yourself to writing x of t as a times the sine of omega t minus phi. And I understand what you're saying, Michael. I understand. You see the other form a lot in physics, but we have to go with what's in our book here, because, you know, I want you to get your problems correct, right, in your homework and on the exam and so forth. Okay, excellent, excellent. Okay, so what I'd like to do, that is just a kind of, that's a little bit of a guided tour of section 5.1, and I think I'm going to show you just a few more figures here. I'm going to show you a few more here. Let me see here. One moment. Because it has a lot of nice pictures too. Okay. Let's see, there's a picture, figure 5.1.4, simple harmonic motion, showing the mass moving up and down. And then you have your corresponding sine wave that models the position of the mass. All right. And then, let me see here. We have some pictures. Wish they were here. Yeah, so this figure 5.1.8 is the motion of what's called an overdamped system. So if the system is overdamped, that means that the mass will eventually come to equilibrium and stay there. The dampening is slowing the mass down so that it won't be bouncing up and down like forever. It's just going to, or whatever it's doing, it's going to just slow down and reach equilibrium over time. That's called an overdamped system. How many have heard of overdamped system in their maybe another class, like physics class? All right, well, if that's okay. All right, okay, different terms. All right, that's fine, thank you. Also, let me see here now. There's something called a critically damped system. So critically damped system is when you have dampening present in the mass spring system, but it's not so strong that the mass basically goes to equilibrium right away. You still have a little bit of oscillatory behavior, but then eventually the mass will reach equilibrium. So this is a critically damped system. I like, you know, this, okay, in figure 5.1.9. And then in figure 5.1.10, you have undamped and underdamped. Okay, undamped and underdamped. Okay, so an undamped system is one that, again, will never reach equilibrium. Okay, and an underdamped system, it will reach equilibrium eventually, but in an oscillatory manner. Okay, so I think these terms are important for you to feel comfortable with this section. And on that note, what I'd like to do is I would like to go ahead and do a few examples with you here. Okay, so let me bring up an example. Are there any questions at all? All right, and maybe I'll just mention something here while we're at it. Okay, thank you, Matthew. Thank you, Matthew. So let me just see here. So again, these differential equations in this section are really applications of section 4.4, what you just learned. So let's go ahead. I want to do a few of the few problems with you here. So let me give you a moment to copy this example down, okay? All right. Okay, I heard something in the chat here. Okay. All right, give you another moment here to copy this down. Okay, so here in this problem, we have a 20-kilogram mass that's attached to a spring, And the frequency of simple harmonic motion is 2 divided by pi cycles per second. If that's the case, we want to find what the spring constant is. And then we want to know what's the frequency of simple harmonic motion if the original mass is replaced with an 80 kilogram mass. So this is a little bit different kind of problem than what, of course you're going to see problems where you have to, come up with the differential equation for the mass spring system based on that standard form of the differential equation in 5.1. Okay, you have to identify the dampening constant, the driving force, the mass, and all that. But I wanted to do a few problems that were a little bit different because I think it'll help you get a comfortable feel. Okay, as opposed, I mean, the standard ones I think you'll be able to do without much difficulty. This one might be a little harder for you. So okay. So this problem here, okay, let's begin. Let me go to the solution. Let's begin with this differential equation here. So that's one of the differential equations from section 5.1. Now what's missing here, of course, is the f of t. Okay, so the most general form of the differential equation on the right-hand side has a plus f of t. But this problem here doesn't mention any external driving force on the mass, so that's why I don't have f of t there. Okay. Now also in this problem, there's also no dampening either. So that's why beta here, is equal to 0. So really, I didn't even need to include this term, really, right? Because this is simple harmonic motion. But I just wanted to show you, hey, dampening coefficient equals 0. So, okay. So the K, of course, the K is, I want to say this the right way. What is the spring constant K? So we're looking to figure out what K is. Okay, we're looking to figure out what K is here. All right, and this here is a homogeneous second order differential equation. What do we need to find to solve that homogeneous differential equation? What special equation is necessary to solve that differential equation for x? Anytime you have a homogeneous differential equation, section 4.4, what? I'll give you a hint. Okay, Mark, you beat me to it. Excellent. Auxiliary, excellent. And that's what we got here. So based off of this differential equation here, we have our auxiliary equation. Okay, and we're going to solve for m, and we're going to get m equals plus or minus I times root k over 20. So what I'm trying to do is get an expression for the position of this mass. And now I've done that. I've done that. This is the equation that models the position of this mass. Now we haven't found what K is yet, but you know. Okay, so let me give you a moment to want to make sure everybody's comfortable. Please let me know if you have any questions. We're not done yet with the problem. Okay, so Paige, the I basically is just, I mean, the coefficient of I, which is square root of k over 20, is what's used here. We don't do anything with the I. We don't do anything with the I. We just take the coefficient of I and put it in for our solution. T is outside of the roots. That's correct, Matthew. T is outside of the roots. Yep, it is. Okay. All right. Are there any questions before we move forward here? All right. Let me ask you, can we find the, so we know that this linear combination here of cosine and sine would be strictly oscillatory behavior. And with oscillatory behavior, can we find, should we be able to find the period for this oscillatory behavior? So the position of the mass goes up and down according to an oscillatory wave. Should we be able to determine the period of that oscillatory wave? Yeah, well, you know, Michael, and of course, the value in the angle, the coefficient of t, is critical for finding the period. I mean, let's just take a little analogy here. If you had the sine of 2x, if you had the sine of 2x, what's the period? What's the period for the sine? Well, for the sine of x, the period is 2 pi. For the sine of 2x, what's the period going to be then? The sine of x, that sine wave has a period of 2 pi. The sine of 2x moves, so that sine function moves twice as quickly. That has a period of pi. That's right, Matthew. And what do? Well, to get that, we take the standard period of a sine wave, which is 2 pi, and we divide it by this 2 here. We divide it by that 2. And so, you know, I have to make use of the frequency in order to figure out what this constant k is. I have to make use of the information regarding the frequency of the harmonic of this mass. It's 2 cycles per pi seconds. So, but frequency can be related to period. So just like the sine of 2x, the period is 2 pi over 2. If I wanted to find the period for my mass as it goes up and down, I can just take 2 pi and divide it by the square root of k over 20. And that's what I do here. The mass is going to have this period. Well, Michael, you know, you know, again, I don't get into W squared and all that. I mean, or omega squared. I know what you're saying. And I'm approaching this from a very simple approach, because some of our students haven't had physics yet, and we don't really need to know physics to do this problem if we go back to the fundamentals. And I like the fundamentals anyway. But certainly the period of this mass would be 2 pi over the square root of k over 20. Okay, now let's I try to make it intuitive. And I like to relate things to things that we've seen before in our math life, because then it makes me feel comfortable. I hope it makes you feel comfortable too. So now the frequency is 2 pi cycles per 1 second, but that can be thought of as 2 cycles every pi seconds. So that means it's going to take pi seconds to do 2 cycles. And so it'll take pi over 2 seconds to do 1 cycle. And so then the period, okay, then for this mass would be then pi over 2, but that is equal to 2 pi over the square root of k over 20 as well. Please let me know if you have any questions. Okay. Are there any questions? You're feeling good? All right, well then let's proceed. Let's proceed. Oh wait, okay, Matthew has a question. Well, Matthew, oh man, I guess I have to go down here a little bit. So, all right, so yes, then we get this step and this step. So square root of k over 20 equals 4. Okay, well then we'll square both sides of this. Square both sides. And you're going to get then k over 20 equals 16. So k is equal to 320. 320. Okay, good. Let me see. Zachary says, is it wrong to substitute square root of k over 20 for 4? What 4 are you referring to, Zachary, in the problem? Yes, it would. Well, now hold on. I'm always careful before I answer. Well, I mean, we do have the square root of k over 20 in the complementary function. The x of t is, since it's a solution to a homogeneous differential equation, the solution to x of t is itself a complementary function, and we do have the square root of k over 20 in there as the coefficient of t in the angle. All right, good question, good question. So now, okay, what is the frequency then if the original mass is replaced with the 80 kilogram mass? Okay, well, 80 kilogram mass. Now I'm going to take the mass of 80 and substitute it back in the differential equation that was at the very beginning. Okay, so 80 times x double prime, which is the second derivative of x with respect to t, plus 320 times x equals 0. Let me just see here. I want to be a little bit careful. Yeah, well, K, hold on one moment, class. Let me just think here for a minute. Yeah, that's right. That's right. This is K now. This is K, 320. So, all right, we just go forward here, and now we, have the auxiliary equation m squared plus 4 equals 0. We solve for m, and so if you have an 80 kilogram mass, you see, we had to find out what K was, right? But now we know what K is. So now this becomes a very simple problem. If the mass is 80 kilograms, that's K there. Here's the mass here. We just solve, and we get this as our solution. And so the period is going to be pi. And so it takes pi seconds to do to do one cycle. And when I say one cycle, that means for the mass to leave its position, okay, and then like let's say the mass goes up and then it goes down and then it goes up again. If the mass goes up, then it goes down and then it goes up again. When it goes up again, when it reaches the same position it started, that's one cycle. I mean, this is one cycle, right? This is one cycle, right? That's one cycle. This is one cycle, right? Okay, so the frequency then is 1/pi cycles per 1 second. Okay, are there any questions on that so far? Okay, very good, very good. One moment, class. Just looking at something real quick here. Hold on. Okay, so in this problem, incidentally, since we had kilograms, the unit of force is in newtons. Okay, but if we are using pounds, and pounds per foot and so forth, if we don't use, I wanted to say this the right way, what's the other measure of force when we're using, well, I want to be a little careful. Let's just get to the next problem, okay? Let's just get to the next problem. Okay, here's another one. Okay, let me give you a moment to copy this down, and then we'll go over the solution for this example. Okay, so here we have a mass of one slug that's suspended from a spring whose spring constant is 9 pounds per feet. And what we want to do is, well, the mass is initially released from a point 1 foot above equilibrium position with an upward velocity of square root of 3 feet per second. We want to find the times at which the mass is heading downward at a velocity of 3 feet per second. Okay, so, all right, so of course, with how many have seen mass of slugs in like that term before? I mean, a lot of people see newtons, but is slug new for some of you? How many maybe have seen that? I don't know, but at any rate, that's the mass when you're dealing with, okay, Christopher has seen it. Good, good. All right. So let's see how to do this problem, okay? What do we have to start with, by the way, to do this problem? What do we have to begin with? Well, what did we begin with in the last problem? Well, okay, Matthew, Hooke's law, but that generates a, I'll give you a hint. It starts with a D. Differential equation. Good, good. Okay. So then, all right. So so we know the spring constant is 9, and we know the mass is 1. And so the differential equation here, and I guess it's going to be 1 times x double prime plus 9 times x equals 0. And oh, well, that comes from 1 times x double prime, okay, equals negative 9 times x. Okay, so the original form of the differential equation is this one. There's no dampening in this problem. There's no external force, and this is based off of Hooke's law. And then that differential equation is this. No, there's nothing above this here. There's nothing above here. This is just the solution. Solution got cut off. Solution. Yeah, solution starts right here. Okay, so here's the auxiliary equation. And from there you get a formula for the general position of the mass, x of t, position function. And of course, we're told that the mass is released from 1 foot above equilibrium position. Well, then that means that initially the position of the mass is -1, because remember, based on the way the axis is, when the mass is above equilibrium position, x is negative. So we're 1 foot above equilibrium position, so x of 0 equals -1. Now we're also told that the mass is released with an upward velocity of square root of 3 feet per second. Well, that means x prime of 0 is -√3. So we have two constants here to solve for, a C1 and a C2. We have two constants to solve for. And we have two initial conditions, so we can solve for those very easily. Okay, and you've done this many times before. And it turns out that x of t is going to equal negative C1 times the cosine of 3t minus root 3 over 3 times the sine of 3t. And those are your C1s and your C1 and C2 values are circled right here. Let me give you a moment to catch up.
Wait, what are you doing in the step right below negative x prime at 0 equals negative quantity root 3?
Let me see, x prime of 0. So, well, C1, all right, so x of 0 equals negative 1.
I mean, like, I would assume you're just solving for C1, but it just looks weird.
That's exactly right. I'm solving for C1. That's right, Matthew. So C1 will equal negative 1. So I put in 0 back into the position function. And the cosine, the sine of 3 times 0 is just sine of 0, which is 0. So, right. And so I solve for C1 and C2, and that gets me to here. Okay, good question. Please let me know if you have any questions.
One more. Does that say in the step right below where you solve for C1, does it say in the first parentheses, does that say it just says negative sine, right? Negative sine of 3t quantity times 3?
That's correct. That's correct. Let me see. Do I have... Right. So I take the derivative of the cosine of 3t, and that is, by the chain rule, negative sine of 3t times 3. That's right. Okay, so now to do this problem, we need to figure out the amplitude and the phase shift. We're going to need that to do this problem. Okay, and so the amplitude is the square root of C1 squared plus C2 squared. And so you're going to get square root of 4 over 3, which is 2 over root 3. Now, how do we find the phase shift? Well, what you do, and again, if you look back in the book, at it's on the recording, but if you look at figure 5.1.3, the coordinates that you plot the coordinates C2 comma C1. Okay, that's the coordinate that you plot. I know you would think it'd be C1 comma C2, but it's not. It's C2 comma C1. So C2 is negative 1 over root 3, and C1 is negative 1. That's in quadrant 3. So the phase shift angle is going to be the angle that ends up in quadrant 3. Okay, and of course you have a reference angle, right? You have this reference angle right here. Well, what I did was I wrote down a right triangle, not worrying about pluses or minuses. I just wrote down a right triangle with sides 1 over root 3 and 1 and 2 over root 3, which mimics this right triangle here, which is for my reference angle. But again, I'm not worried about the plus or the negatives and positives. And if you multiply this right triangle by root 3 on all sides, you'll end up with this right triangle. And that's very recognizable as a 60, 30, 90 degree right triangle. So I did that just because I think, at least when I took trig, this was like the triangle I always used, But of course, if you're, but I'm just trying to show that, why is this triangle a 30, 60, 90 triangle? It's because if you multiply all the sides of the triangle by root 3, you get this triangle, and it has sides 1, root 3, and 2, and that's recognizable as a 30, 60, 90 degree triangle. And now, based off of that, you're able to determine that the phase shift phi is going to be 4 pi over 3. In other words, it's going to be, let me see here, one moment. It's going to be, yeah, it's going to be 180 degrees plus 60 degrees. Okay, may I move to the next page? Are there any questions? And we won't have time. You'll have to refer, I think, probably to the recording for this last part. But let me go ahead to the next page. We know our phase shift now. And now x of t is equal to 2 square root of 3 times the sine of 3t plus 4 pi over 3. So that's your phase shift phi. Now, in the problem, you want to find the times at which the mass is heading downward. Okay, well, so we want to find, we want to find the times at which the mass is heading downward at a velocity of 3 feet per second. So velocity means take the derivative of position, and that's what I do. I take the derivative of position to get my velocity, and I set that, and I simplify it, but that I set equal to 3. Okay, that I set equal to 3. Well, that means then that the cosine of 3t plus 4 pi over 3 would have to equal root 3 over 2. If I divide both sides of this equation here by 2 over root 3, okay, I'll get cosine of 3t plus 4 pi over 3 equals root 3 over 2.
What is the times root 3 doing in the step right below where you say downward velocity equals 3 one? Like the first thing after you, like
this 2 over root 3 here?
No, multiplied by 3. So in that same term, or in that same line,
The chain rule. The chain rule. Good question, Matthew. The derivative of
sorry.
No problem. It's a good question, and I'm sorry if I might go over a few minutes. It'll be in the recording, but I do my best. Okay, so all right. So okay, we want to know, when is this angle here? When is this angle here? Okay, when would the cosine of that angle equal root 3 over 2? Well, that's going to happen. That's going to happen when our angle, well, the cosine of pi over 6 of 30 degrees equals root 3 over 2. And the cosine of 330 degrees will equal root 3 over 2. Because the cosine is positive in the first and fourth quadrants. And so based on that, if my angle here is equal to pi over 6 plus 2 times n over pi, where n is an integer, I can solve for t. Okay, this is an n. That's correct. That's correct, Zachary. This here is an n. Okay, because they want in the problem, find the times at which the mass is heading downward, and so we want to find all the general times. 2n pi. That's exactly right, Zachary. Similarly here, if 3t plus 4 pi over 3 were equal to, if that were equal to negative pi over 6 plus 2n pi, that would also then satisfy this condition above. That would satisfy this condition above. And if you solve that, you're going to get t equals negative pi over 2 plus 2n pi over 3. It got a little bit cut off here, but this is 2n pi over 3. And that's how you do this. That's how you do this. Okay? That's how you do this. Okay, and I thank you for your patience. Now, I'll mention, are there any questions in general before I mean, I know you're maybe copying a little bit, but are there any questions in general before I stop the recording? Okay, very good.